Hi, everybody. Welcome back to Dave's Math Channel. This is my continuing feature on the Math Lovers book, and now I'm starting a new section, section 2.9 of volume 1, and that's on magic squares. So let's begin. So I have a couple of videos already on magic squares. You might want to watch those first, but this is just an overview of what magic squares are. Um, standard magic squares use all the numbers from 1 to n squared. You have an n by n, it's a square array. So I'm going to define a magic square as a square array or matrix, if you like, of numbers from 1 to n squared. So for instance, 3 by 3 would be the numbers 1 through 9. 3 by 3 turns out to be the smallest possible magic square. And this one's called a Lo-Shu square. This is actually very famous. It's very old. This was discovered in China around 2800 BC, I think. And there's a legend. There's even some documents showing a turtle. There was supposed to be some mystical turtle that had one of these Lo-Shu squares on its back, on the shell on its back. And I'm not sure exactly what the significance was to the Chinese, but it's a pretty amazing square. I mean, if you just look at it, and what makes it magic, by definition, a magic square is a square array of numbers from 1 to n squared, such that every row, every column, and every long diagonal has the same sum. And in this case, the sum is 15. For a Lo-Shu square, it's pretty easy to see that the sum of the numbers in every row, every column, and the two long diagonals is equal to 15. You can check that yourself. But what's interesting about the Lo-Shu square to me is that it turns out this is the unique 3 by 3 magic square. We're using just the numbers 1 to 9. I mean, there are other magic squares. You skip numbers or you use numbers with certain properties, but we're not doing that here. We're just using the numbers 1 through 9 and not counting rotations or reflections. I guess there's total of 8 possible squares you can get if you rotate or reflect about different axes, but we're not counting those as distinct. If you don't count those as distinct, this is the only one. So it's unique. That's kind of a nice feature of the 3 by 3 Lo-Shu magic square. But what about bigger ones? What about 4 by 4? 4 by 4 are trickier. I mean, 3 by 3, it wasn't, I guess it wasn't that hard to discover the 3 by 3 magic square because, there's not that many possible places to put the numbers. But 4 by 4 is a lot harder. But it turns out it's no longer unique if you do 4 by 4. Whereas there's only one up to rotations and reflections for 3 by 3. It turns out there's a total of 880, believe it or not, for 4 by 4. And the number grows astronomically after that. I think it's only been calculated up to 5 by 5 how many essentially distinct magic squares are. And already for 5 by 5, it's already in the millions. Maybe even the billions, I don't know. It hasn't even been calculated for bigger than 5 by 5. So the number of possible magic squares grows astronomically. They're not that rare, it turns out, but they're still kind of hard to find just because there's so many possible places you could put the numbers. I mean, for a 4 by 4, you got 16 numbers. That's a total of 16 factorial. That's a huge number. It's already in the billions. Those are the number of possible places you can put the 16 numbers. Even though there's only 880 magic ones, if you just did this randomly, probability you get a magic square is very, very low, probably like 1 in a million. But there's a special one. They're not that hard to find, it turns out. I'll show you how to construct a 4 by 4 after this. But the most famous 4 by 4 magic square was discovered by a pretty famous, I think he was Dutch polymath named Albrecht Dürer, or maybe German. I think he was German, actually. He lived around the same time as Leonardo da Vinci. In a lot of ways, he was kind of similar to Leonardo da Vinci. Not only was he an artist, he was also an amateur mathematician. And I guess one of the things he was interested in was magic squares. So he actually discovered, it's now called a Dürer square. And the magic's constant for 4 by 4 squares, including the Dürer squares, turns out to be 34. So you can check yourself if you add the numbers in every row, every column, and the two main diagonals, you get 34. And not only that, it turns out I think there's something like 40 other possible ways you can get 34. I mean, you could take any group of four numbers that make up a little square, like 16, 3, 5, and 10. That is a 34, the four numbers in the upper left corner. I have another video on this. I'm not going to go over every possible, but I think every 2 by 2 block like this, of which there's I think 9, those all add to 34. Not only that, if you take the four corners, add up to 34. I think if you take the four corners of any subsquare, you get 34. Or if you take like the numbers in the middle of a row, like 5 and 5 and 9 are in the middle of the first column, 8 and 12 are in the middle of the fourth column. You have those up, you get 34. You can do reflections out like 3 and 2 and 15, 14. You can play around with this. You get tons and tons of ways of getting 34. And I think there's a total something like 40 possible ways to get 34. So it's got a lot. I mean, it's not just a magic square, but it's kind of super magic. It's got a lot of sums that add up to the magic constant, not just the ones that make it magic, but a lot. And another thing that's really cool about this version of the Durr square is unique up to rotations and reflections. Not only that, if you look at the two numbers on the in the middle of the bottom row, 15 and 14, 1514, that was the year he constructed this square. Pretty remarkable. So, and I guess he was so proud of this construction he made that he actually I have to go back. I didn't put these in order, but he made a work of art called Melancholia 1. This is a pretty famous work of art he made. And he has a lot of, I mean, the Dürer square in this, it might be kind of hard to see. I think it's an angel sitting on the right side of the picture. If you look above his head, above his wing, there's the Dürer square in the upper right corner. A little hard to see at this magnification, but it does have the same numbers I just showed you. And that's not the only mathematical thing he put in this picture. There's a kind of a complicated polyhedron on the middle left. I don't even know what that's called. Like a truncated, I think it's a truncated hexahedron or something. And there's a lot of others. An hourglass symbolizing the passage of time, I guess, and a bunch of other references to mathematics. So he was really interested in math. And keep in mind, this was back in the early 16th century, so a long time ago. And I'm gonna go back to where I should be here. So that's the Dürer square. What about bigger magic squares? Like I said, I think these are out of order. I'm going to come back to how to construct a 4x4. But it turns out, like I said, there's magic squares of every order, and there's even nice, easy ways to construct them. There was a kind of another amateur mathematician, Simon de Loubert. I believe he was part of the one of the king's court. I think he was like on some king's high court. I can't remember whose. I think it was 18th century France. And he actually came up with a general method for constructing a magic square of any odd order. Not even order, but odd order. And it's a pretty simple method. Maybe I can describe it here. So I think what was used for the 5x5 and 7x7. Yeah, if you look at the 1, notice the 1 in the top left is a 5x5 magic square. 1 is just one square below the middle, below the 13, which is right in the middle. Then you go down to the right, down and to the right, put the 2 there. Go down and to the right, but you have to wrap around because you can't go down any farther than the bottom row, so you wrap around to the top row. And then one space to the right, that's where you put the 3. Keep going like that. Down the right again, wrap around to the left side, you get a 4. And then you do that again, you get the 5. But then you do something different. Once you've gotten 5, you go down 2 steps. So notice that's 2 steps below the 5 is the 6. Go down and to the right again, put the 7 there, down to the right again, 8 and 9, 10. Down 2 squares again, wrap around 11, 11, 12, 13, 14, 15. You can see those numbers are all on the main diagonal going down and to the right. And then do the same thing with 16. Go down 2 squares, BF wraparounds, get the 16 on the right. Keep going down to the right, 17, 18, 19, 20. And so you think you see how that works. And then down 2 squares again, 21, down to the right, 22, 23, 24, 25. You're done. And that turns out to be a magic square. So that's kind of the recipe. It also works for 7 by 7. Unfortunately, it doesn't work for magic squares of even order. Those are trickier. And there is a nice method for 4 by 4. I'm not going to go over a general method for arbitrary magic squares in even order, because those are hard to construct in general. I even know how to do them except for 4 by 4. But here's a nice easy way to construct a 4 by 4 magic square. Start with just take a 4 by 4 square, write the numbers in order on the square, like lexicographically. 1, 2, 3, 4 in the top row, and then like you're reading a book or writing on a book. Start on the left, the second row, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Easy. So you write all the numbers from 1 to 16. Now the second step is you erase the numbers in the middle of every row and column on the edge of the square. So you erase the 2, 3, 5, 9, 8, 12, and 14, 15. You're left with just the numbers in the middle and the numbers on the outer corners like that. And now what you do is you count backwards. So to get the final step, the way to fill in the blanks here is you start with a 16, but you count that as 1, and now you do everything backwards. So now you're going to the left on each row. You're going to the left and up instead of to right and down. So you would write a 2 next to this 16 and a 3 next to that. And then if you do it that way, you'll end up with this square here. And this is a magic square. You can check yourself. This is a 4 by 4 magic square. It's kind of close to Durer's square. I think if you reflected about the center the horizontal axis, you might actually get the Durer square, something close to it. But it is a magic square, and you can check for yourself that it is a 4 by 4 magic square with the same magic constant, 34. And by the way, the magic constants for a standard n by n magic square, the magic constants are always the same, and they're even easy to calculate. I don't remember the formula offhand, but it's easy to calculate. I think it's something like n times n squared plus 1 over 2, if I'm not mistaken. Yeah, I think that is the formula. But anyway, that concludes my video for today on magic squares. So thank you for watching. Long live math, and I'll see you guys next time.